Now we move to electrochemistry because we can also make semiconductor junctions in electrochemistry and use them for solar cells. So in electrochemistry, we have the contact of an electrode and a solution. And here at the surface of the electrode, there can occur a redox reaction. So this cell, for example, is making an oxidation reaction at one side and reduction of silver at the other, so that this is going to produce a voltage. So when we put the electrode, it has the Fermi level of electrons in the metal. And in solution, there's also a Fermi level, and this is called the redox level. So the redox level is characterized by a standard value and a value that depends on the concentration of reduced and oxidized species of the redox pair. So that since there is exchange, there will be achieving equilibrium, and in this case, this happens by making here an interfacial layer, which is called the Helmholtz layer. So that in this case, there will be an equilibrium between the metal and the electrolyte. We have seen the energy scale for electronic quantities in materials with respect to the vacuum level. And then we can tabulate all the work functions, etc. And we also have seen the methods to measure this. But in electrochemistry, there is a different reference. And the reference is actually a reaction, the reaction of the reduction of hydrogen on the platinum electrode. So the difference between the two scales is the energy of the hydrated proton. So this is minus 4.44 electron volts. So that at the right is the electrochemical energy, and at the left is the electron energy. So the energy of the redox pairs can be put into the electrochemical scale, and this can be made in connection to the work functions and to the energy levels of semiconductors in the electronic energy with respect to the vacuum. So in this way, when we take a semiconductor and we put it in contact with a redox couple in an electrochemical cell, there is an exchange of electrons and they come to equilibrium. So it will form a barrier at the interface. And when we bias this barrier, for example, by putting a negative voltage here, then we will modify the height of the barrier. So in this situation of the applied bias, now we can see a step of the Fermi level, and this is always the indication that the system is not equilibrium, and if charge can flow because there is this acceptor in solution, then charge which will flow. This actually at forward bias, so electrons will start to jump into the solution and we will get a current. And here we can do the also corresponding to the change of the work function of the metal. Here we can change the redox energy in the electrolyte. And if we change the electrolyte and make a higher one, then this will come to the other equilibrium, and we will have a reduction of the interfacial barrier. Also in the semiconductor electrolyte interface, we can have the surface dipole, and the surface dipole is going to change the alignment of the energy levels between higher or less high barrier depending on the amount of interfacial dipole. So here is a change of dipole with different work functions, and then this is showing the change of the barrier represented in the open circuit voltage. We consider N-type semiconductor, and here redox electrolyte that is situated very deep, close to the conduction band. Then what is going to happen is that we will have this band bending at the surface and also the valence band. But now this material, which is N-type, here is depletion, and here is not N-type because the Fermi level is close to the valence band, so here it's P-type. So there is an inversion layer where the type of semiconductor has been inverted at the surface, and this can induce the injection of holes better.